Welcome to the course on power quality. So, we are discussing the examples on shunt active power filter. So, this is the 8th example. A 3-phase shunt active power filter is employed with the reactive power compensation for 3-phase 3-wire 415 volt 50 Hz system. A set of non-linear load consists of Thyristor bridge and diode rectifier connected in parallel, and the diode bridge converter is drawing 100 ampere constant DC current. Thyristor bridge converter is drawing 75 ampere constant DC current at 30° fire angle of its thyristor. Calculate the current rating of the active power filter to provide a harmonic current and reactive power compensation at unity power factor. Let the supply is stiff enough so that the distortion in the voltage at the point of common coupling is negligible. This is the system that is a composite load, consists of diode rectifier and thyristor converter, and we are using it like at the point of common coupling 3-phase active filter. So, after making the model, I mean these are typical waveforms of 3-phase grid voltage, then the load current, the supply current, and then 3-phase load current, then a 1-phase current of the active filter, then the DC link voltage, and of course, the diode side current of the your diode rectifier and thyristor converter line. Coming to numerical part of the solution of this problem. So, given that the supply voltage of 415 volt by root 3 to 39.6 volt, frequency 50 hertz. The diode bridge converter is drawing 100 ampere constant DC current, and thyristor bridge converter is drawing 75 ampere at 30° fire angle of its thyristor. So, in 3-phase diode bridge converter, the RMS of Cauchy square load current is ISD equal to ISD into root 2 by 3. So, that comes 81.65 ampere. Moreover, the RMS of fundamental component of Cauchy square wave is your ISD 1 equal to root 6 by pi into IDC, that is 77.97 ampere. And moreover, the active component of AC current of diode bridge rectifier is ISDA, that is ISD 1, that is 77.97 ampere. And in case of the second part of the load, that is in case of thyristor bridge converter, the IST is root 3 by 2 by 3 into IS DCT, and that is comes like a typically or 61.24 ampere. And moreover, the RMS fundamental component of Cauchy square current IST 1 is root 6 by pi into IDCT. So, this becomes 58.48 ampere, and the active component of thyristor converter input current is your ISTA cos theta 1, that is IST 1 cos alpha, and putting the value here for alpha and current, this comes 50.64 ampere. Therefore, the total active power component of supply current of both the loads are ISA 1A, that is by diode rectifier, this is current by thyristor converter, it comes by addition of both 128.61 ampere, and therefore, ideal supply current will be your reactive current will be like your IS 1 cos sin theta, that comes like your typically 28 into sin theta, and we can find out what will the filter current. I mean therefore, the RMS current of shunt filter is computed with the half wave symmetry. I mean like typically for 2 upon 2 pi means half cycle. So, start from typically first 60° you have this kind of current, then the next typically I mean it is a from pi by 6 to alpha, and this is from pi by 6 alpha to 5 pi by 6, and this is 5 pi by 6 plus alpha, and this is from 5 by 6 plus alpha to pi, and the RMS current for this comes like your after this it comes your filter current comes 37.24 ampere, and the voltage across the filter, I mean that is the point of common coupling voltage, this is Vf equal to Vs, and that is 239.6 volt. So, VA rating of the active power filter will be 3 Vf IF, and it is a 3 into 239.6 into 37.24. So, it is say like your 26,771.25 VA. So, now coming to another example, example number 9, a 3-phase shunt active power filter is employed for current harmonic current compensation of a 3-phase 415 volt 50 hertz fed 12 pulse diode bridge converter drawing 400 ampere DC current. It consists of an ideal transformer with single primary star connected winding and 2 secondary winding connected in star and delta with the same phase voltage and unity turns ratio to provide 30 degree phase shift between two sets of 3 phase output voltage, and two 6 pulse diode bridges are connected in series to provide 12 pulse AC DC converter. Calculate the active power drawn by the load, the current, voltage and VA rating of the active power filter to provide harmonic current compensation at unity power factor. So, these are typically a load of 12 pulse thyristor converter or diode converter with the series connection, and this is the shunt active power filter for compensation of this load. And these are the typically the after the model, these are the simulated waveform supply voltage, then we have a supply current after the compensation, and these are the typically the you can call it the load current, which is a sum of typically these are the your filter current, then the DC link voltage, then the output of converter, and that is the output load current. So, coming to the solution, given that the supply voltage per phase will be 415 by root 3, that is 239.6 volt 50 hertz, and the DC side current is 400 ampere. And in 3 phase 12 pulse diode bridge converter, the waveform of input AC mains current is a stepped waveform. At first step of pi by 6 angle is from 0 to pi by 6, and input current magnitude is IDC by root 3, and second step of pi by 6 is from pi by 6 angle, and that is pi by 6 to 2 pi by v, and the input current magnitude is IDC 1 plus 1 by root 3, and the third step of pi by 6 angle is from pi by 3 to pi by 2, and the input current magnitude is your 1 IDC into 1 plus 2 by 3, and it has a all 4 symmetric segment of the such step. Therefore, the RMS current of the 12 pulse converter input current will be IS, that IDC, taking RMS of typically of all the 3 segments which we already mentioned, like virtually it comes like 1.557, and this comes 630.94 ampere, and the RMS of fundamental current of 12 pulse converter input is your IS1 2 into root 6 by pi IDC. So, this is your 1.559 393 IDC. So, this comes 623.797. So, active power done by the load will be P equal to 3 Vs IS1 cos theta 1, and putting the value here theta 1 is because of diagonal rectifier, it comes like 448.358 kilowatt, and hence the total RMS harmonic current will be, which is a current for flowing into the active filter, IF equal to IH and under root IS square minus IS1 square. So, it comes 94.934 ampere, and the voltage rating of the filter is voltage across the filter VF Vs, that is 239.6 volt, and the V rating of active filter is VF IF. So, putting the value of like your 3 into 239.6 into 9 pi 94.934. So, it comes like your rating 68.239 kVA. So, now coming to on 10th example, a 3 phase shunt active power filter is employed for harmonic current and reactive power compensation for 3 phase 415 volt 50 hertz 12 pulse Thyristor bridge converter, drawing a 400 ampere constant DC current at 30 degree fire angle of its Thyristor. It consists of an ideal transformer with single primary star connected winding and 2 secondary winding connected in star and delta with the same line voltage and UT turns ratio to provide 30 degree phase between the 2 sets of 3 phase output voltage, and 2 6 pulse Thyristor bridges are connected in series to provide 12 pulse AC DC converter. Calculate the fundamental active power drawn by the load, fundamental reactive power drawn by the load, V rating of active power filter to provide only harmonic current compensation, only reactive power compensation, full harmonics current and reactive power compensation at unity power factor. Let the supply is stiff enough so that the distortion in voltage at the point of common coupling is negligible. So, this is the typical circuit. We have a 12 pulse Thyristor converter with series connection, and we have a shunt active filter which is connected at the point of common coupling to provide the harmonic compensation and reactive power compensation. And this is the typical waveform of supply voltage, supply current after compensation. These are the 3 phase load current of converter. These are active filter current, which not only have a harmonic current, but also typically the reactive power current also, and this is the DC link voltage regulator of the active filter. So, given that the supply voltage per phase is Vs equal to 415 by root 3 to 39.6 volt and frequency 50 hertz and IDC 400 and fire angle is 30 degree. So, in 12 pulse in 3 phase 12 pulse Thyristor converter bridge converter, the waveform of the input AC current is a step waveform. The first step of pi by 6 angle from alpha to alpha pi by 6 with the input current magnitude IDC by 3, and second step from of pi by 6 angle from alpha pi by 6 to alpha pi by 3 and the input current magnitude is IDC 1 plus 1 by root 3, and the third step of pi by 6 angle is from alpha plus pi by 3 to alpha plus pi by 2, and the input current magnitude is IDC 1 plus 2 by 3 into IDC, and it has a all 4 symmetric segment of such a step. So, moreover, the RMS current of 12 pulse, I mean a fundamental AC current is IS1 to root 6 upon pi, that is IDC. So, it comes 1.559 623.5757, and total harmonic current will be that IH equal to IS square minus IS1. So, putting the value here, it comes 94.934, and active power component of supply current will be IS1A, that is IS1 cos theta 1 or IS1 cos alpha, and 623.757 into cos 30, it is like a 540.19 ampere, and the total harmonic current, harmonics and reactive current will be IF IS1 square minus IS1A square, and putting the value of this, it comes 326.01 ampere like. And the fundamental active power drawn by the load will be 3 Vs1 IS1 cos theta 1. So, that is 3 Vs IS cos alpha, and it is a 388.289 kilowatt like. And fundamental reactive power drawn will be your Q1, that is 3 Vs IS1 sin theta 1, and it comes like a, after putting the value 224.17 kVr. So, V rating of your active power filter to provide only harmonic compensation, that is current rating equal to current flowing into the filter, that is IF equal to IH under root IS square minus IS1 square. So, putting the value, it comes 94.934, and voltage rating of the voltage rating of active power filter, voltage across the filter, that is same as the PCC voltage, that is Vf equal to 239.6 volt, and the V rating of active filter is 3 Vf IF, that is 3 into 239.6 into 94.934. So, it comes 68.2386 kVA. Only reactive for active power filter rating, only for reactive power compensation, for that current rating is equal to filter current. So, that is IF equal to reactive current, that is IR equal to IS1 sin theta 1, and that is equal to IS1 sin alpha, that is 623.757 sin 30. So, it is a 311.87 ampere, and the voltage rating of the filter is equal voltage across the filter, that is Vf equal to Vs equal to 239.6 volt, and V rating of active filter is your 3 Vf IF, and that is 3 Vs IS1 sin theta. So, it comes 224.172 kVA. Now, the active power filter rating for providing the harmonic current and reactive power compensation. So, the filter current will be IS square minus IS1A square, putting the value, it comes 326.01 ampere, and the voltage rating of the filter is voltage across the filter, that is Vf equal to Vs equal to 239.6 volt, and the V rating of active filter for this component 3 IF, that comes after putting value 234.336 kVA. So, you can clearly see there that all 3 compensation have a rating is increasing, I mean from one to another like. So, coming to numerical number 11, a 3 phase with a line voltage of 415 volt 50 hertz, 4 wire distribution system, 3 single phase loads connected between phase and neutral, having a dot bridge converter drawing a equal constant 25 ampere DC current. A 4 lag VSI with the DC bus capacitor is used as a active power filter. Calculate A, load neutral current, B, active power filter phase current, then the C, active power filter neutral current, D, kV rating of the active power filter to provide harmonic current compensation at unity power factor. Let the supply is stiff enough, so that the distortion in voltage at the point of common coupling is negligible. So, this is the typical load. We have a 3 phase 4 wire load with the diode rectifier with the RL load, and this is a 4 lag shunt active filter to provide the your harmonic compensation as well as neutral current compensation like. So, after making the model, these are typical waveform of 3 phase supply voltage, 3 phase supply current, and the supply neutral current, the 3 phase current, neutral current, then the active filter current for 3 phases, and DC link voltage and load side current. So, coming to numerical part of the solution, given that the supply voltage is your Vs equal to 239.6 volt and frequency of supply 50 hertz and DC link current is 25 ampere. So, in the single phase diode bridge rectifier, waveform of the supply current is a square wave with a amplitude of DC link current. So, moreover RMS value of fundamental square wave is 2 upon pi times these amplitude of the current like 0.9 times that. So, therefore, the RMS current equal to IDC, that is 25, and fundamental current RMS will be 2 root 2 upon pi into IDC, that is 0.9 IDC, and comes out 22.5 ampere. So, current rating of the active filter will be current flowing through the filter, that is IF IH, and that is IS square minus IS1 square, and putting the value it comes 10.897 ampere. And the voltage rating of active filter will be same as the phase voltage, Vf equal to Vs and 239.6 volt, and the load neutral current is 25 ampere. It will also be square wave of 3 times the fundamental frequency, and the phase current rating of the your active filter will be If equal to IH, Is square, Is1 square, it comes 10.897 ampere, and the active filter neutral current will be the same as the load neutral current, that is 25 ampere. And since it has to cancel total load neutral current, and V rating of active filter will be 3 times Vf into Vf and that will be typically putting the value here of this. So, it comes 13.822 kVA. So, coming to the another 12th numerical problem, a 3-phase 4-wire distribution system with line voltage of 415 volt 50 Hz feeding the 3 single phase loads connected between phase and neutral, having a set of diode bridge rectifier drawing a AC current at 0.92 displacement factor, and THD of the AC current is 60%, is drawing 2000 watt from the AC source, and crest factor is 2.5 AC of input current. A 4 lakh voltage source in inverter with the DC bus capacitor is used to realize the 4-wire shunt active filter. Calculate the current voltage and V rating of the active power filter to provide harmonic current compensation, reactive power compensation, harmonic current, and reactive power compensation at unity power factor. So, this is typically the load now. After diode rectifier you have a RC load, and this is a 4 lakh your active power filter to provide the harmonic compensation as well as the neutral current elimination. So, after making the model and simulation, these are the waveform of supply voltage, supply current, which are at unity power factor and balance and sinusoidal, and because of that neutral current is made 0 in the supply like here typically. And these are the 3-phase load current on 3 phases. This is neutral current, and this is the 3-phase typically the current of this shunt active filter, and this is the DC link voltage. So, coming to the solution part of it, given that a 3-phase line voltage of 415 volt 50 Hz, 4-wire distribution system, and supply voltage is 415 by root 3, and that is equal to 239.6 volt, and frequency is 50 Hz, and total harmonic distortion is 60%, displacement factor is 0.92, crest factor is 2.5, and active power is 2000 watt on each phase, and there is a single phase diode rectifier load connected between the phases and neutral. And in the single phase diode rectifier bridge converter, the fundamental active power component of supply current is as IS1 equal to PS divided by Vs, that is 8.347 ampere, and the RMS fundamental supply current will be your IS1 A divided by dPf. So, putting a value, so your RMS fundamental current comes like 9.073 ampere, and the distortion factor is df equal to 1 plus THD square, so it comes 0.857 ampere, and the power factor is df into dpf, so it comes 0.789. Moreover, RMS supply current will be power divided by your Vs into Pf, so it comes like putting the value 10.58 ampere, and the APF neutral current will be equal to load neutral current, that is root 3 times Is, so it will be 18.325, since it has to cancel total neutral current, and V rating of active power filter will be only for harmonic compensation, it will be If equal to IH, ISC square minus IS1 square. So, putting the value of this, it comes 5.411 ampere, and the voltage rating of course across the filter is same as the PCC voltage, that is 239.6 volt, and the V rating of active filter will be 3 VFIF plus VFIFM. Putting the value of these, it comes 8.302 kVA. Now, only for reactive power compensation, the current rating of the filter will be equal to reactive current, that is IR equal to IS1 cos sin theta 1, and that will be IS1 under root 1 minus dPf square, so it comes 3.556 ampere, and the voltage rating of the filter will be voltage across the filter, that is your Vf equal to Vs to 39.6 volt, and the V rating of active filter with 3 VFIM plus VF. So, putting the value, it comes 6.946 kVA. Now, coming to harmonic current and reactive power compensation. So, IF equal to IS square minus IS 1 A square, putting the value it comes 6.501 ampere, and the voltage rating of the filter is voltage across the filter, that is Vf equal to Vs equal to 239.6 volt, and the VA rating of active filter with 3 VFIF plus VFIM. So, putting the value of all this it comes 9.064 kVA like. Now, coming to the numerical problem 13, a 3-phase with line voltage of 415 volt 50 Hz, 4-wire distribution system, 3 single phase loads connected between the phases and neutral, having a set of single phase uncontrolled bridge reactive wire which have a RE load with resistance of 2 ohm, and the voltage of battery is 264 volt. A 3 leg VSI with the midpoint DC bus capacitor is used for neutral current compensation to realize as a 4-wire shunt active filter. Calculate A, fundamental active power, B, voltage, current and VA rating of active power filter to provide unity power factor. Let the supply is stiff enough so that distortion in voltage at the point of common coupling is negligible like. So, this is the system that we have a battery charging load for all 3 phases equal with the 2 ohm resistance in series, and this is the 4-wire, you can call it 4-wire shunt active filter. 3 is, but neutral is connected with the midpoint of capacitor. So, after designing and simulation, these are the 3-phase voltage, 3-phase current, and neutral current of supply is made 0, and these are the 3-phase load current and neutral current of the load, and 3-phase your 3 shunt active filter current, and typically the load current term like. So, coming to numerical part of this, given that supply voltage Vs equal to 239.6 volt, and the peak is of this 239.6 into root 238.85, and frequency of supply is 50 Hz, and load resistance is 2 ohm, and your E equal to 264 volt. So, in the single phase out bridge converter with RE load, the current will flow from angle alpha of AC voltage is equal to E and to the angle beta at which the AC voltage reduces to E. So, we can find out alpha equal to from this relation, so it comes 51.179 degree, and beta comes 5 minus alpha 128.82 degree, and the conduction angle beta minus alpha will be 77.641. So, this is going to conduct for this angle out of 180 degree in 1/2 cycle, and the RMS current in RMS supply current is the RMS of discontinuous current of AC main. So, from the relation we can find out typically the RMS current it comes 17.84 ampere, and the average current in the battery will be your IDC equal to from this relation, that is if you put the value it will be 10.67 ampere, and the active power done by from the AC mains will be ISC square R plus E IDC. So, it comes like a 3453.94 watt, and fundamental RMS current from AC mains will be IS1 equal to P upon Vs, that comes like a typically 14.415 ampere, and the current rating of active filter is current flowing into typically in the phase lag. So, IF equal to IH and equal to IS square minus IS1. So, this is 10.522 ampere, and the active filter neutral current is your same as your IF equal to ILN, that is root 3 IS. So, it is typically your 30.94 since it has to cancel neutral current, and the voltage rating of active filter will be corresponding to same as PCC voltage 239.6, and the KV rating of the filter will be 3 VFIF plus VFIFM. Putting the value all these it comes like your KV rating equal to 14.998 kVA. So, coming to now fourth numerical problem, a 3-phase line voltage of 415 volt 50 Hz, 4-wire distribution system, 3 single phase loads connected between phases neutral, having a single phase Thyristor bridge converter with the equal current of 30 ampere constant DC current at a 45 degree angle of the Thyristor, and 4 leg VSI with the DC bus capacitor is used as active power filter. Calculate the current, voltage and VA rating of active power filter to provide a harmonic current compensation, harmonics current and reactive power compensation at unity power factor. Let the supply is stiff enough so that the distortion in the voltage at the point of common coupling is negligible. This is the typical system that diode rectifier with typically Thyristor converter with your this load, and this is your typically the shunt active filter with the load current also. So, giving the supply voltage of 239.6 volt and frequency of 50 Hz and DC link current of 30 ampere and fire angle of 45 degree. So, in a single phase Thyristor bridge converter, the waveform of supply current is square wave with the amplitude of DC current, and moreover the RMS of 1 component will be your 2 root 2 of pi, that is 0.9 times the amplitude of the current. So, therefore, RMS current will be IS equal to IDC 30 ampere and fundamental current will be 2 root 2 upon pi into IDC, that is 0.9 IDC equal to 27 ampere. And the RMS fundamental active power component will be your IS1 equal to IS1 cos alpha. So, putting the value alpha 45 degree, so you get 19.092 ampere, and load neutral current will be your typically same as 30 ampere, because since it also will be a square wave of 3 times of fundamental, and active power filter fourth lag current will be IFN equal to IL, and that is 30 ampere, because since it must be opposite to the load neutral current to cancel it, and VA rating of the active power filter will be for harmonic compensation. The current rating will be through typically IF equal to IS square minus IS1 A square, putting the value it comes 13.077 ampere, and the voltage rating of this is equal to VF equal to 239.6 volt, and VA rating will be 3F VIF plus VF IFN. After putting value it comes 16.558 kV. For a harmonic current and reactive power compensation, IF will be IS square minus IS1 A square, and this will be your 23.141 ampere, and voltage rating of this will be of VF equal to VS equal to 239.6 volt, and VA rating of active filter will be 3 VF IF plus VF IFM, that is 23.822 kVA. So, coming to the numerical problem 15, a 3 phase with line voltage of 415 volt 50 Hz 4 wire distribution system, 3 single phase load connected between phase and neutral having a resistive heating element of 15 ohm through a phase control AC controller with the fire angle of 60 degree, and a 4 lag VSI with the DC bus capacitor is used to realize as a 4 wire shunt active filter. Calculate A, fundamental active power drawn by the load, fundamental B, fundamental reactive power drawn by the load, and C, the VA rating of active power filter to first to provide only harmonic compensation, second only reactive power compensation, and third harmonics and reactive power compensation at unity power factor. Let the supply is stiff enough so that the distortion in the voltage at the point of common coupling is negligible. So, this is the system that we have a 3 single phase AC voltage controller, and this is the your 4 lag you can call it like a shunt active filter to provide reactive power and harmonics and to make the neutral current 0. After making the model, these are the simulated results: supply voltage, supply current, and the neutral current in supply becomes 0, and these are the 3 phase load current. These are the typically the load neutral current, and opposite of this will be your shunt fourth lag current, and this is your 3 phase current of shunt active power filter with DC link voltage of shunt active filter to be regulated like. So, coming to numerical portion of this, given that the supply RMS voltage is Vs equal to 415 by root 3 to 39.6 volt, and frequency of supply 50 Hz, and resistance is 15 ohm, and fire angle is 60 degree. So, in the single phase control AC controller, the waveform of supply current has value of Vs by R from angle alpha to pi, and where the VSM is peak voltage of 239.2 into 2, that is 338.84856 volt, and RMS supply current will be IS equal to VSM with this formula of single phase AC controller. So, it comes 14.3267 ampere, and the fundamental RMS current will be IS1 from the derived relation for single phase AC controller, it comes 13.4044 ampere, and the you can call it the your angle between fundamental voltage fundamental current will be from this relation it comes minus 16.53, because it is a behave as a lagging power factor load, and the RMS fundamental current from the supply will be active power component of will be IS1A, IS1 cos theta 1, it after putting value it comes 12.85 ampere, and hence the total RMS harmonic current will be IS equal to IS square minus IS1 square, and putting the value it comes like 5.0573 ampere, and RMS reactive power component of the supply current will be IS1 R IS1 sin theta 1, and putting the value it comes minus 3.814 ampere like, and total harmonics and reactive current will be IF equal to IC square minus IS1 square under root of that, putting the value it comes 6.335 ampere, and the fundamental active power done by the load will be PA1 equal to 3 Vs IS1 cos theta 1, that is 9236.59 watt, and fundamental reactive power done by the load will be 3 Vs IS1 sin theta 1. So, it comes like 2741.35 VR. So, V rating, now we have to calculate volt ampere rating of the active power filter only for harmonic compensation first. So, current rating will be equal to current flowing through the filter phase. So, that is IF equal to IS square minus IS1 square under root of that. Putting the value of this, you get the 5.0573 ampere, and the active power neutral filter neutral current is same as the minus of load current, that is root 3 times IS. So, it comes like root 3, so this comes 24.815 ampere. So, it has to cancel the total neutral load current, and voltage rating of the filter will be Vf equal to 39.6 volt, and the VA rating will be 3 Vf IF equal plus Vf IFM. So, putting the value, it comes 9.581 kVA. So, coming to the shunt filter rating for only for reactive power compensation. The reactive power equal to 3 P sin theta 1 upon cos theta 1. So, it comes like your 2741.81 VR. Current rating of filter current will be equal to reactive current. So, IS that IF will be IR equal to IS1 sin theta 1, and putting the value of this, it comes 3.814 ampere, and the voltage rating of the filter will be voltage rating across the PCC, that is Vf equal to Vs2 39.6 volt, and the V rating of active shunt filter will be S equal to 3 Vf IF plus Vf IFM, and putting the value, it comes S equal to 8.668687 kVA. Now, coming to the active power filter, shunt active power filter rating for harmonic current and reactive power compensation, IF equal to IF IH, and that will be IS square minus IS1 square. Putting the value, it comes 6.334 ampere, and voltage rating of the filter is same voltage equal to your Vs equal to F 39.6 volt, and VA rating will be 3 Vf IF plus Vf IM. Putting the value, it comes like 10.499 kVA. So, with this we will like to summarize this shunt active power filter, and shunt active power filter are used for to compensate the power quality problem of harmonic currents, reactive current, fluctuating current, unbalanced current, and excessive neutral current produced by the nonlinear load. And shunt active filter offer the best solution for current fed type and mixed type of load, current fed and voltage fed kind of nonlinear load with moderate rating, and PWM based voltage source inverters are used preferred to realize the shunt active power filters because of low cost, reduced size, light in weight, and reduced losses like. And a passive ripple filter is used at the point of common coupling, where the shunt active filter is connected to improve the voltage profile and to eliminate the higher order harmonic which shunt active power filter cannot eliminate. And this passive small passive ripple filter does not have much losses, even being sometimes damp type, because of energy associated with the higher order harmonics is quite small. However, these higher order harmonics either produced by nonlinear load or due to switching of shunt active power filter cause disturbance to communication system and other electronics appliances like. An analytical study of various performance indices of shunt active power filter for compensation of nonlinear load is made in detail with several numerical examples to study the rating of power filter and how it is affected with the nature of the various kind of nonlinear load. Shunt active power filter are observed one of the best retrofit solution for mitigating power quality problems due to nonlinear load for reducing the pollution AC mains. And there are references, these are the some references which we have followed, and thank you very much. So we like to close this shunt active filter like.